In order to build our interpreter, first we're going to have to parse the input text into an abstract syntax tree that we can actually do something useful with. In order to do that, we're going to have to specify the language that we're dealing with formally by building a grammar. If you took Foundations of Computer Science, you may remember context-free grammars as something that was mentioned there, and that's exactly what we're dealing with here. So in order to define a grammar, we actually write it down in Backus-Naur form, or BNF, which is a standard way to define grammars, at least for computer programming languages. And that looks kind of like what you see on this slide. As you can see, there's 3 different rules here. First, we define that an expression is either a number or an expression, an operator, and an expression. So for example, an expression might be the number 1, or it might be the number 1, the symbol plus, and the number 5. And this is recursive, so this can go as deep as it needs to go. A number in this case is just some natural number, and in this slide I'm not showing some specific rule for that, but when we're specifying a grammar to a computer, we'll have to say that a number is a sequence of 1 or more digits, or something like that. And then finally, an operator is one of the 4 operator symbols from a 4-function calculator. And once we have a grammar like this, that's defined the syntax of a language. And if we give a grammar like this to a computer, it can actually give us an abstract syntax tree automatically. So when we give the computer that has built a parser for us from a grammar an expression like 1, as shown here, it'll go ahead and see that 1 matches the number rule, which is one of the cases for the expression rule, and so we get this parse tree, which we can also call an abstract syntax tree. Those are both words for the same thing. And this is what we'll work with when we're actually evaluating an expression. This is the simplest case. A more complicated case is when we have an expression like 1 plus 4. So this is an expression because 1 is an expression because it's a number, and 4 is an expression because it's a number. And 1 plus 4 is an expression because it matches the second case of the expression rule. It's an expression, an operator, and another expression. So in writing that parse tree, we can write it in this simpler way that's a little bit clearer to read and not include all the intermediate steps. And this is the abstract syntax tree that we'll actually be dealing with in software. So one of the things that matters is exactly what tree we get out of the parsers that we build. And that will depend on exactly how we specify the grammar. Using the grammar that we had built there, if we take an expression like 1 plus 3 times 7, it'll parse as shown in this slide. First, it will parse 1 plus 3 is a valid expression, and then it will make that the left-hand child of the subtree where that result is multiplied by 7. And this isn't quite what we want because of order of operations. We actually want to do the addition first and the multiplication second, because multiplication is higher precedence than addition. So in order to do that, we're going to have to reformulate our grammar in a different way. In this case, all we have to do is separate out different precedents of operations. We can have 2 separate rules for expressions, or 2 separate rules for operators. One for low precedence operators called low op here, and one for high precedence operators called high op. And then we need 2 separate rules for expressions. And we're going to call an expression with a high precedence operator a term. And this is actually pretty common in the literature, so if you see term, this might be what that means. And we specify that a term is either a number or a term, a high precedence operator, and a number. And then we specify that an expression is either a term or an expression, a low precedence operator, and a term. And this will do the right thing. When we go ahead and parse that same expression using a parser generated from that grammar, we'll get this tree shown here where the multiplication binds tighter than the addition. And then when we go to evaluate this tree, we'll recursively descend down the tree, and we'll do the multiplication first because it's closer to the leaves of the tree. So when we go to take this parse tree that we've built and call it an abstract syntax tree, we're going to label the pieces. We're going to remember that the leaf nodes in this case were numbers, and the interior nodes were operators, as we can see here. This is convenient when we go to actually build the software, because we can do pattern matching and say, if we see an operator, we do an operator thing, and if we see a number, we can just realize that the value of the number 1 is 1. So here's the section quiz, and once you successfully get this question right, you can go ahead and watch the next video on the theory of how we will do evaluation of these abstract syntax trees that we've built.